the city that you see in my background, and which is, by the way, the birth town of Albert Einstein. I'm a member of the editorial board of Springer Nature PDEA, and it's my great pleasure to chair today's webinar and introduce our today's speaker, Professor Markus Melenk. Markus started his scientific career at the University of Maryland at College Park, where he received his master and also his PhD. University of Maryland, for people in numerical mathematics, this rings a bell. In fact, both Markus' master and PhD thesis have been supervised by Ivo Babushka, who will turn 95, if I'm well informed, on March 22nd this year. Dr. Melenk then moved to Switzerland, where he worked as a postdoc in the group of Christoph Schwab and received his habilitation at the ETH Zurich in the year 2000. After acting professorships in Regensburg, Kiel, and Chemnitz, all Germany, Markus moved to the Max Planck Institute in Leipzig and then as a reader to the University of Reading. Since 2005, he is professor of computational mathematics at the Technical University in Vienna. Professor Melenk is a world-known expert in numerical analysis. His work bridges between the analysis and numerical approximations of wide classes of PDEs and gave deep insights into their close connection, in particular with respect to regularity of solutions and its relation to convergence speed of numerical schemes. His work has drawn significant attention with about 2,800 citations in the Math Synod. Today, Professor Melenk is going to speak on high-order numerical methods for fractional diffusions in polygons. Markus, the floor is yours.
Thank you very much, Carsten, for your kind words. I'd like to thank also the organizers for giving me the opportunity to present some of my recent work here. And I'd like to acknowledge my co-workers in this research, Lehel Banyai from Harriet Watt and Christoph Schwab from ETH Zurich. And in the last part of the talk, I will talk on extension to time-dependent problems, and that is joint work with Alexander Rieder from the University of Vienna. Okay, so here's the outline. So after an introduction, I will say a few things about, fairly elementary actually, about approximation on geometric meshes. Then I will present two methods. So the first one is a Galerkian method for the extension problem, the so-called extension problem. And the second method, localization 2, is a solution, is based on discretizing a solution formula for the problem. And then the last part, I will talk about extensions to time-dependent problems. Okay, so what is fractional differential operators? So they became popular in recent years, and I think the reason is that sort of applications drives them. So if one wants to describe anomalous diffusion, if one wants to solve problems in computational finance, in material sciences, or in image processing, it turns out that fractional differential operators are actually a powerful tool to model these phenomena. So what is the fractional Laplacian? So in full space, there are several essentially equivalent definitions. So the first one is maybe the best known one. It's in terms of Fourier transform. So you take the Fourier transform of a function, you apply its symbol, you multiply by its symbols, psi to the 2s, and then you transform back. So that would be a natural definition of the fractional Laplacian in full space. There's another one by singular integral, as a singular integral operator, so as hypersingular integral operator to be precise. Or you could view it as a Dirichlet to Neumann operator for an elliptic problem in a half space. So that's the Caffarelli-Silvestre extension. Or you could use the Danforth-Taylor calculus. We will also do that. There are even more definitions. In bounded domains, and this is of course what we are interested in here for computational purposes, there are these definitions extend, but not necessarily in an equivalent way. So there are two particular cases. The first one is the integral fractional Laplacian, where one simply restricts any of these definitions to a bounded domain. And then there's a second case, and that is the case of interest here. That is the so-called spectral fractional Laplacian. That means one starts from eigenfunction decompositions of the operator of the integer operator, so the Laplacian, and uses that spectral decomposition to define the spectral one. So I give you more details about the spectral fractional operator here on this slide. So we are looking at L to the SU equal to F with Dirichlet conditions, and the differential operator L is minus divergence matrix A grad U, where A is a uniformly symmetric positive definite operator. The whole thing takes place in omega, which is a polygon. And we assume that A is smooth. In fact, I will replace A by the identity matrix in a minute. Okay, so how is this operator defined? As I said, we use a spectral decomposition. So the phi k and lambda k are the eigenpairs of the differential operator L, and we normalize them. And then the application of the differential operator L to the S is given by this formula. And it works like that. So you take a function u, you decompose it in the eigenfunctions, phi k times scalar coefficients uk. And then the action of L to the SU is simply a sum over all k, eigenvalue lambda k raised to the power s, coefficient uk times the eigenfunction phi k. Okay, so with this definition, this problem on top here is easily solved. If you decompose f in the eigenfunctions, then the solution u is simply the sum of all k uk phi k, where the uk is given by lambda k to the minus s times f. Okay, so we have a solution formula already, and you may wonder, so what's the big deal about numerical methods? Well, in practice, of course, the eigenfunctions are not known to us, so this definition is not really numerically tractable. This problem comes with energy, with spaces hs or h sigma, and they are simply given by sort of decay conditions on the coefficients when you expand a function in terms of the eigenfunctions. So this is here the formal definition. For relevant to us will only be three cases. Sigma equal to 0 corresponds to the L2 space. Sigma equal to 1 corresponds to the space H1 0. So the zero boundary condition is encoded here in this eigenvalue problem. And the case sigma equal to S corresponds to the energy space of this elliptic problem. So in fact, the L to the S is HS elliptic. And as I said already, we will focus here on the case matrix A is Laplace, is identity, so we are looking at the fractional Laplacian. Okay, so what is the goal of today's talk? So I want to design numerical methods based on differential operators, so on local operators. And I want to discuss high order methods, and in particular, I'm shooting for exponential convergence for piecewise analytic data. As I said already, I will do that for two different types of methods. And I want to highlight here one key thing one unifying theme for these two different discretizations. And that is the meshes that I will use are geometrically refined towards vertices and edges. So in this 2D case here with a smooth boundary, so you see you have meshes that are fairly dramatically refined towards the boundary. So they're long, thin elements. And here in the case of polygons, you have the same thing. Here you have these small, thin elements, but near the boundary, you actually have further geometric refinement towards the corners in order to resolve corner singularities. Okay, so let me start with something very simple about geometric meshes. So the first question that I want to discuss is, why should I care about high order methods? So this is a very simple question. Let's say I have a smooth function here, this black curve, and I want to approximate it with, let's say, a piecewise linear function. So I do here piecewise linear interpolant, or I want to approximate with a higher order polynomial. So in this particular case, a polynomial of degree 4, and I chose a Chebyshev interpolation. So already qualitatively, you see that the polynomial of degree 4 is a much better approximation than this piecewise linear one. Okay, so a complete error analysis for this kind of interpolation is of course available. So for the piecewise linear approximation, the error scales like h squared, where h is the mesh spacing of these interpolation knots. So that leads to algebraic convergence. So the error in some norm here is n to the minus 2, where n is the number of knots that we had here. So you had 1, 2, 3, 4, 5, 6, 7, 8. In the Chebyshev interpolation, so if you have smooth functions, then you get e, for example, 2 to the minus p, something that is even smaller, times the p plus first derivative of f. So as p grows, so this goes to 0 very quickly. So you can actually expect exponential convergence in the polynomial degree. Okay, so that tells you that higher order approximation could be very accurate, and indeed quantitatively you see that here. So for example, if you want to have with a piecewise linears an error of 10 to the minus 4, you need something like 200 knots. So while you for 2 to the 10 to the minus 4 here with Chebyshev interpolation, you get by with less than 9, polynomial degree 9, so 10 points. Okay, so you clearly see the advantage of higher order methods. Okay, so is there a catch? Well, you see that here in the error estimate. So you need, of course, for polynomials degree p, you need, of course, higher order derivatives. So what happens when that is not the case? So for example, if we try to approximate the function x to the alpha, where alpha is between 0 and 1, then the function is, of course, not smooth at x equal to 0 because derivatives will blow up. And then a Chebyshev interpolation, it does not work so great. So actually you see an algebraic convergence of 1 on p. So the reason is that the function is not smooth. So what should we do? Well, the answer is on the next slide. If I still want to have good approximation by polynomials, I should use piecewise polynomial approximation on appropriate meshes. And these are the so-called geometric meshes that will appear frequently in this talk. And this is why I want to sort of spend some time on that. So here we have the 1D case. So we approximate the function x to the alpha, say, and we know that the singularity is at x equal to 0. So we need to refine the mesh there in order to resolve that singularity. So for example, on the next mesh, we refine, and then so by splitting into 2. And then we refine again by splitting again into 2, but only the left element. And then we refine again, but only the leftmost element, and so forth. So a geometric mesh, more generally speaking, with L layers and grading factor sigma is given by the points, this left endpoint 0, and then sigma to the L, sigma to the L, sigma to the L minus 1, and so forth up to sigma to the 0, which is 1. Okay, so these are the meshes. So they're strongly refined towards a point. So how should we approximate by polynomials? Well, let's say on the coarsest mesh, we use polynomials of degree 1. On the next mesh, we will use polynomials of degree 2 on each of these sub-elements, and then 3 on each of these elements, and so forth. So you see, we simultaneously increase the approximation order, the polynomial degree, and refine the mesh near one point. And for this case then, so for x to the alpha, this piecewise Chebyshev interpolation actually converges exponentially in the polynomial degree p. And the number of nodes, so the number of unknowns that we have for this interpolation problem is p times p plus 1. So the number of elements times the polynomial degree, the dimension of polynomials of degree p. And here's then a plot. So we have the error versus the number of knots. And here this red curve tells you shows you that you really get this exponential convergence in the polynomial degree p. Okay, so that extends to 2D. So this is why the geometric mesh idea sort of generalizes to 2 and higher dimensions. So for example, in elliptic problems in 2D, the typical solutions have corner singularities. So the solution behaves like r to the alpha times something smooth. And r is the distance from a point, let's say a vertex of the domain. If you want to do the approximation there, you do a geometric refinement towards that troublesome point. You see here, so it's a self-similar refinement towards that point. So the elements near the singularity are again very, very small. And by selecting L proportional to the polynomial degree, you get exponential convergence. Edge singularities, this is a sort of an archetype of this, is something similar. Let's say in 2D, you have a function of x and y, and it's smooth in x, but you have a nasty y dependence, so it's y to the alpha. In that case, again, you do a geometric mesh refinement towards the edge y equal to 0 so you do a geometric mesh in one direction and a node mesh refinement in the other direction. So you get these anisotropic elements. Again, you get exponential convergence. Okay, so these was a long prelude on geometric meshes. Let me start now with the first numerical method, based on the Caffarelli-Silvestri extension. This is So what is the Caffarelli-Silvestri extension? So we enter in the function u on this domain omega. Let's embed this omega by increasing the dimension by 1. So we extend it into R3, and omega is now simply the bottom of an infinite cylinder C, which is omega cross 0 infinity. Okay, and the extra variable that we introduce now is called y in the rest of the talk. Okay, so we have this infinite cylinder, and we will seek a function capital U on this infinite cylinder. So there will be a relation between the function little u, this function that we are interested in, the function capital U, and that is that u is the trace on the bottom of the cylinder of the function capital U. So what happens to capital U? Capital U solves an equation, Lu equal to 0 in the cylinder, and L is an elliptic operator. So it's minus divergence of y to the 1 minus 2s grad U. So it's an elliptic, U solves an elliptic equation. Okay, so we need to satisfy here these boundary conditions. This is accounted for by saying that requiring that U is 0 on the mantle of the cylinder. And we somehow have to bring in the data f, and that is that the conormal derivative of U on the bottom of the cylinder is up to a scaling factor ds, the function f. So, and this is the Caffarelli-Silvestri extension. So what do we know about the function U? I've written that down here once more. Think for a moment about the case s equal to 1/2. Then 1 minus 2s is 0, so you see that actually capital U is harmonic. It solves Laplace's equation. And more generally, actually, you expect that U is analytic in the cylinder, simply because the coefficient y to the 1 minus 2s is analytic. It's an elliptic problem in a corner domain because we have here these edges, also here on these green edges. And so you expect algebraic singularities at the edges and vertices of the cylinder. And you also, since the coefficient y to the minus 2s degenerates, you expect an algebraic singularity at y equal to 0. Okay, so a lot of these things are simply expectations. So what can one show? So for example, the analyticity in the function, in the variable y, can be shown explicitly. So here's the reference. So, and this is the theorem that comes with it. So why does that theorem tell us that it's analytic? So you see the function capital U, if you take the Lth derivative, then it behaves like L factorial. And that happens for all natural numbers L. So that is a hallmark of analyticity. Another thing that we know is that actually it decays exponentially in y. That is what this factor tells us. There's an algebraic singularity at y equal to 0. You see that here in this highlighted term, because for each differentiation for the Lth derivative, you have y to the minus L. So each time you differentiate, you pull out a factor 1 on y. Okay, one knows a little bit more about the solution behavior. So for example, the trace on omega, so the function little u, behaves like the distance to the boundary raised to a power that is not an integer. So here's a picture of what that looks like. So you see the typical algebraic edge singularity of the solution. So that is what's known. How should we discretize? How should we solve for u? Well, we follow here this reference and do a classical finite element method on the cylinder. So the bilinear form that comes with it is given here. It's simply obtained by multiplying by test function and integrating by parts. There's an energy space that is simply given here by those functions that have finite energy. So the bilinear form AC is finite, and we need to incorporate the boundary condition, so the vanishing on the mantle. So this is its function H1 circle. Okay, the variation formulation is then completely classical. So it's given here by this expression. And the Galerkin method is also fairly simple. You simply replace the infinite dimensional space H1 by a closed subspace Vn. And this is a nice elliptic setting. So actually one has quasi-optimality in this energy norm. So the finite element solution UN exists, is unique, and its error measured in the energy norm is the minimum over all possible approximations from the finite element space Vn in the energy norm. And remember that ultimately we're interested in the trace. So we need to relate the energy norm to a norm on omega, but we have a trace estimate. So the HS norm is actually bounded by the energy norm. So convergence in the energy norm tells us something about convergence in the energy norm. Okay, so sorry, this quasi-optimality result tells us that we only need to worry about the selection of the space Vn. How should we choose it? And we will choose it as a tensor product. So it is a tensor product of a space of piecewise polynomials of degree p on a mesh T, which lives here in omega, tensorized with a space of piecewise polynomials of degree p on a mesh GL that lives on the 1D interval 0 curly a y. Okay, so let's first focus on the mesh GL-GU. We know that the solution decays exponentially in y. So that's good news, because that means we can simply cut off at some point curly y and probably not make a big error. The next thing we know is that the solution has a singularity at y, and it's an algebraic singularity. So from the prelude, we know that a geometric mesh refinement towards y equal to 0 is a good choice. So this is the mesh GL-GO that we will use for the rest of the talk. So the interval 0 curly y is discretized with a mesh with L layers, so L plus 1 elements. So the smallest element is sigma to the L times y, and so forth up to sigma to the y, and then y. Okay, so this is the space that we will use. So the question is, how should we choose the mesh in omega, so the T? So morally speaking, we know already what's going on, because we know that we should capture these algebraic singularities, these edge singularities near the boundary of omega. So we expect geometric meshes to work well. Technical trouble is that we don't have a full regularity theory for the solution of the extended problem. So this is why we proved an exponential convergence result in a different way. So so this is the finite element space that we want to use. To motivate the correct choice of space, SPT, so of the triangulation T, let's look at the semidiscretization case first. So let's replace the SPT by the infinite dimensional Sobolev space H10. Okay, so and then this is again a closed subspace. So the U semi will be the Galerkin approximation to the function U. Okay, and then one can show this is essentially the analyticity of the function U and the exponential decay, that actually the semi-discrete approximation error is bounded by these three terms. So the first one is exponential in the polynomial degree p, so that is this p here. The second term is exponential in the number L of layers of the geometric mesh here. So essentially e to the minus b prime L is related to the size of the smallest element here by at y equal to 0. And the third term here, e to the minus b double prime curly y, is related to the cutoff. that we make an error by simply cutting off. But that error is small, as you see. Balancing these three terms tells us already how we should choose curly y, L, and P. They should be proportional to each other. So that will fix for the rest of the talk the relation between curly y, L, and P. Okay, so here's again the geometric mesh that we will use, the semi-discrete space. I want to get my hands on the semi-discrete solution. So on this U semi, I want to get my hands on it. For that, it is clever to actually find a good basis of this space SPGL. Okay, so for that we solve an eigenvalue problem. You'll see on the next slide why this is a clever choice. So we saw the VI's and the mu eigenvalues mu i's solve this eigenvalue problem. So it's a 1D eigenvalue problem on the interval 0, y. Okay, here you recognize here, of course, the weight that comes with the extension problem. And we normalize things here. Okay, so what I'm plotting here in the left curve is the eigenvalues mu I of this eigenvalue problem. For the case of a geometric mesh with 12 layers and polynomial degree 12. So you have roughly 100 eigenmodes. And I'm plotting them here, their value over the number. So, and you see that most of them, so they ranges from 10 to the minus 20 to essentially 1. So you see that most of the eigenvalues are very, very small. Okay, one can quantify that. Here's a quantitative estimate. So the mu i's are between L squared and sigma to the 2L. So this is essentially the square of the smallest element in the mesh GL. Okay, so we have these eigenvalues, these eigenfunctions, VI. So now we make the ansatz that the semi-discrete solution is unknown functions UI, which live in H1, 0, times these piecewise polynomials VI of Y. Okay, now one can compute, it's a fairly elementary calculation that the UI satisfy this differential equation, or this variational formulation. So mu I times the integral over grad UI, grad V, plus the integral over UI times V is V times F times V, the integral over F times V. Okay, so this is a variational problem. You see it's an elliptic problem for the UIs. Essentially it is minus mu I Laplace U plus U equals F. And now you notice that the mu i's, most of them are small. So this is actually a singularly perturbed problem. Okay, it is convenient to abbreviate this bilinear form here. And the next thing, we are of course not interested in the semi-discrete approximation. Ultimately, we are interested in the fully discrete Galerkin approximation. And then it's a calculation that the fully discrete approximation, so the approximation from the space SP of T tensorized with SP of G, has this form. So the UN is the sum over PI UI times VI, where the PI's are simply the Galerkin approximations of the functions UI in the space SP of T. So they satisfy this best approximation property. So that is, in a way, we have a solution formula for the fully discrete problem, but in terms of the semi-discrete approximation, because so the semi-discrete approximation, then we apply a Galerkin approximation to that, and then there we have the fully discrete approximation. So it's numerically also interesting that we have a nice decoupling technique. But for our purposes here, we see that actually this formula tells us how we should choose the mesh. Namely, we should choose it in such a way that the PI of UIs can approximate well the solutions UI. And remember that the UIs are solutions of elliptic problems of singular perturbation type. So ultimately, we have to design the mesh such that we can solve, then we can approximate a bunch of singularly perturbed problems well. And the range of the singular perturbation problem of parameter is fairly extreme. So it can be 10 to the minus 15 down to size 1. Okay, so we've reduced things to understanding solution of singular perturbation problems. I've done that in my life. So let's look at first the problem of a single scale. So we look at minus epsilon squared Laplace u plus u equal to f. So here's the 1D case. So the typical solution behavior for smooth right-hand side is like that. So you have a smooth solution, and then in a small O of epsilon neighborhood, you have a sharp layer. Okay, so how do you resolve that numerically? Well, you probably need a small element of size epsilon near the boundary layer, so at the left endpoint and at the right endpoint, in order to resolve that layer. If you approximate with piecewise polynomials of degree p, a good choice is actually to have this width p times epsilon. If you do that 2D, then the correct mesh looks like that. So you have, let's say, a coarse mesh elements, and then here you have a long, thin element, where the width is again p times epsilon. The reason why you need long, thin elements is that these boundary layers are essentially, or the troublesome effects are 1D. So they vary sharply in the direction normal to the boundary, but they vary smoothly in the direction tangential to the boundary. So this is why long, thin elements are a good choice. For corner domains, things are a little bit more complicated. So you need, again, for example, here these long, thin elements, and near the vertices, you need to resolve the corner singularities. And this is what happens here on an O of p times epsilon neighborhood. There you need a geometric mesh refinement, as I've shown you in the prelude. So again, it's self-similar refinement towards the corner. So what you see here is a blow up of this region. If you do that, you get exponential convergence in the polynomial degree on these kind of meshes, uniformly in the singular perturbation parameter epsilon. Okay, so this is the single case, scale case. What happens if epsilon is in a range of between epsilon min and 1, say? Well, of course, you need, in some sense, you need to use the union of all these meshes. And the way to conveniently realize that is you do geometric mesh refinement towards the boundary. So for example, in the 1D case, you do a geometric mesh with the smallest element being sigma to the L, where the L is chosen such that sigma to the L resolves the smallest length scale. So it's proportional to epsilon min. And then it is at least plausible that sort of for each epsilon that is between epsilon min and epsilon 1, you have a mesh that looks like that, sort of that this is a finer mesh than the one that you would need. Same thing in 2D, you would use a geometric mesh refinement towards the boundary with the smallest element be having width sigma to the L. And I'll tell you something about what happens in corner domains on the next slide. Okay, and then one can show that the HP finite element method converges again exponentially in the polynomial degree P in the energy norm, uniformly in the singular perturbation parameter epsilon. Okay, so how should we use design meshes for corner domains? The simplest case is, of course, a square. Then one would use a tensor product mesh. In the general case, so for example, here for this L-shaped domain, I would propose to construct these meshes via mesh patches. So you start with a coarse triangulation, like here, and then each of these elements is subdivided further. So each of these patches. So for example, let's start with this one here. So you want a geometric refinement towards here, this boundary edge. So you do that here by geometric mesh refinement towards the edge. So what happens here at the corner? So you have two edges. So you need to do geometric mesh refinement towards both edges. And so you use, in a way, a tensor product of geometric meshes. This corner here, so there's a singularity here. So you need a geometric mesh refinement towards the singular point. And again, we've seen that self-similar refinement towards that singularity already. And then there's a last kind of patches. You need a transition between the boundary layer patch and the corner patch. And this is what I call the mixed patch. So it is simply meant as a transition between this one and this one. And the other elements, sort of their inside, are not refined anymore. Okay, so let's go back to our Caffarelli-Silvestri extension problem. So we are going back now to the fractional diffusion problem. So if we use, let's say in 1D, the mesh T that is geometrically refined towards the endpoints, or in 2D, let's say a geometric mesh that is geometrically refined towards the boundary, then, and this is the finite element space that I use now, so piecewise polynomials on these geometric meshes, tensorized with the SP of GL. So this is the discretization, the mesh in the Y variable. Then one can actually show, this is here from this reference, if the geometry is smooth, 1D or analytic, then one can actually show exponential convergence in the polynomial degree, if the polynomial degree is chosen proportional to the number of layers and proportional to the cutoff parameter Y. Okay, so this is exponential convergence in P. If you check what the problem size is, so the Vn, then you find out that it's P to the spatial dimension plus 3. So in 2D, for example, this is P to the 5. In corner domains, so in polygons, so they're not strictly 2D, you need to do the geometric refinement towards edges and vertices. So for example, here, if this is the boundary, and then this is the mesh that we would use, so you do a geometric mesh refinement towards the edges, and here near the vertex of the domain, you do a geometric mesh refinement towards the vertex. Then you get again exponential convergence in the polynomial degree, P, and the problem size now is P to the 6 rather than P to the 5. Okay, so we calculated this also numerically. So what I'm plotting here for the, let's say, the square domain. So you see here the mesh that we use, the error in the energy norm versus the polynomial degree P for different values of S. And you clearly see exponential convergence in the polynomial degree. I should say that the numerical results are obtained with ngSolve, developed by Joachim Schöber and his group in Vienna. We did also calculations for an L-shaped domain, and here for a slit domain, and qualitatively you see the same thing, exponential convergence in the energy norm. Okay, I want to tell you a few things about the second method, the so-called sync quadrature method. So this is now a new method. Starting point is here an idea of Bonito and Paszak to start from a representation formula for the solution. So if the function little u that we seek has actually the form L to the minus f times S times f. So we have the solution operator S, L to the minus S has this form. So it is an integral over lambda identity plus the differential operator, which is here the fractional, which is the Laplace operator to the minus 1. Okay, so one can rewrite this integral. So how should we discretize that? Well, we start with discretizing the integral. So and the simplest thing to do is to do a discretization with the trapezoidal rule. So this infinite integral from minus infinity to infinity is trapezoid on a uniform mesh with m+1 points. The quadrature points yj are j times m to the minus 1/2, and j runs from minus m to m. So in other words, it's a uniform mesh with spacing 1 over square root of m. Okay, and then the approximation to this solution operator is q to the minus s, which is simply a finite sum of solution operators for elliptic problems. So it's identity plus epsilon squared Laplace or minus Laplace raised to the power minus s. And the epsilon is given by this formula here. Okay, of course, when one discretizes, the semidiscretization incurs an error, but the error is actually exponentially small in the number of quadrature points. So it's e to the minus square root of m. So in other words, that is under control. So here's again the solution formula. Of course, for a fully discrete method, one needs to discretize these solution operators. So in other words, one needs to solve elliptic problems, and we do that by a high order finite element methods. So by a piecewise polynomial approximation by polynomials of degree p on a mesh T. So how should we choose the mesh T? Well, so we are discretizing an elliptic problem, identity plus epsilon squared times Laplace. Now these epsilons here, here's the formula. Most of them are small, or at least the troublesome ones are small. So we need to be able to solve singularly perturbed problems. Now I've told you already how to do that. We can do that with geometrically refined meshes where the meshes are anisotopically refined towards the boundary. And this is what one can do. And then one obtains a scheme that converges exponentially in P, so in the appropriate norm. If we do the two things, the first thing is that for the discretization of the geometry T, so of the omega, we use a geometric mesh with L layers of refinement, where the number of layers of refinement is proportional to P and proportional to square root of M, because e to the minus square root of M over 2 is the smallest length scale that is induced by the quadrature. And of course, we need now to remember that we have an error here, e to the minus square root of M. So we need to balance errors. So square root M should be proportional to P. If you do the bean counting, then actually the problem size for smooth domains is also P to the 5. And for polygons is also P to the 6. So it's the same problem size as previously. We did some numerics for this. So here are some for the certain parameter choices. We computed the error. We did not compute the HS error, but we computed something similar to the energy norm error that we use for the first method. So it's the integral of f times exact solution minus numerical approximation. So we plotted the error here versus the polynomial degree, and you observe again exponential convergence here for the square domain. You may wonder, is this better than the first method? So here I'm plotting for the same polynomial degrees the convergence of this first method, so the Galerkin method. And it seems like the Balakrishnan formula here, so the second method, is slightly better. But one should be careful here with comparing parameters. So for this particular choice of parameters, if one plots the error versus the number of linear systems that one actually has to solve. So for example, here for this Balakrishnan formula, we had a bunch, for each quadrature point, we had to solve an elliptic problem. So these are fully decoupled problems. And a similar decoupling trick can be done here for the Galerkin method. So a fair measure is really the number of linear systems that one has to solve for. And then actually, at least for this parameter choice, the Galerkin method comes out slightly better. We did the same calculation here for the L-shaped domain and for the slit domain. We compare again here the Balakrishnan formula with the Galerkin method, and also for the error versus number of linear systems that need to be solved. So the same, qualitatively the same behavior as for the square domain happens. Okay, the last few minutes, I want to switch topic and talk about time-dependent fractional problems, because these techniques that are developed here for the elliptic case extend to the time-dependent problems. So the first case is here actually the fractional heat equation. So you have u dot plus the fractional Laplacian applied to u equal to f. It's a spectral fractional Laplacian here, and so we apply Dirichlet conditions, and of course we need initial conditions. So at t equal to 0, we impose condition 0. So of course we know how to discretize the fractional Laplacian. So how do we deal with the time dependence? Well, essentially one can use any kind of time discretization technique. So we in particular use actually a DG method in time, but you could also do a Runge-Kutta method if you wished. Okay, so what is the new feature here? The new feature here is that at time t equal to 0, one actually has a a singularity that is typical of these parabolic problems. So one needs to do again a mesh refinement towards t equal to 0. And what we propose here, following here Schötzer and Schwab, is actually to do a geometric mesh refinement towards time t equal to 0, because the solution has an algebraic singularity there. A fractional time derivative with gamma being not an integer. Like in the Balakrishnan formula, one actually has a solution formula, and this is the solution formula. It's maybe a little bit daunting, but I'll go through the step by step. So the first thing is that just like in the Balakrishnan formula, one has a contour integral. So that's an integral that essentially goes from minus infinity to plus infinity. And we will use again a sinc quadrature for that. So just like in the elliptic case, that integral is discretized with a sinc quadrature. Then we have here these objects E gamma 1 and E gamma gamma. Those are Mittag-Leffler functions. So the entire functions explicitly known. So in a way, they are under control. The next object here is the Z plus Laplace raised to the -1. So these are, of course, elliptic solution operators for elliptic problems. And the choice of the contour here is such that these lead to singularly perturbed problems. So when we discretize this elliptic solution operator, we use that with the techniques that we've seen before. Anisotropic refinement towards the boundary is the key thing. And then here for the inhomogeneity, there's another integral in the time derivative, in the time, so from 0 to t over tau. And here's again an algebraic singularity that can again be dealt with an HP quadrature in the tau variable. So in other words, we have the techniques that we've developed earlier in this talk can actually be combined to get an exponential convergent scheme. And this is what can actually prove. So if the geometry is analytic, the initial data is analytic, and F is analytic, and we do the appropriate mesh refinement. So T is refined towards the boundary geometrically, and the sinc quadrature has p-squared quadrature points, and the tau discretization is done with an HP quadrature. Then one gets exponential convergence in P. And this is a numerical example where one sees the exponential convergence. Okay, so let me wrap up. I've shown you two discretization techniques. The first one was increasing the spatial dimension by 1 and using a standard Galerkin method on this infinite cylinder. So one uses a geometric mesh that is refined towards Y. And on omega, one uses meshes that are anisotropically refined towards the boundary. And in polygons, one needs to do additional refinement towards the vertices of the polygon. And then one gets exponential convergence for the fully discrete problem. The convergence is root exponential, so e to the n to the minus 1/5 for smooth domains, and e to the n to the minus 1/6 for polygons. And the second discretization was we discretized first a solution formula with a sinc quadrature, and then the resulting decoupled singularly perturbed problems are solved with high order finite element method. We use for those the same geometrically refined meshes as for the previous method, and we get the same exponential convergence results. Of course, I should say here that parameter B is not the same one, but sort of qualitatively one gets the same convergence result. And for these elliptic solvers can be used to you design solvers for parabolic problems, so particularly for the fractional heat equation and for time fractional problem. And with that, I conclude my talk. I thank you very much for your attention. And here are a few more references about the things that I talked about today. Thank you very much.
Thank you, Markus, for this very, very nice talk, exactly in the flavor of what I said before, bridging between analysis and numerical schemes for difficult problems. And the presentation is open for questions. Anton, you simply Are you unmuted? No, not yet. I think you can unmute yourself. Is that correct, Stanley?
He says that he doesn't have a mic, so I guess we'll have to just read the question in the chat. Can you see it, Markus?
No, sorry.
Given that BK and HPFEM errors appear pretty similar, which is more performant in the sense of wall clock time to solution?
I think they were fairly similar in wall clock time. So, because ultimately, these are, well, no, they are not similar because one has, for the HP method, one has fewer problems to solve. But of course, I mean, these are the number of linear systems that one has to solve. I mean, they're completely decoupled. So this is completely, can be done in parallel. So it is not as critical as it may sound. Because, okay, I mean, here the difference is between, let's say, 20 and 40. So it's a factor 2. So it's not that critical. And in the end, these problems are fairly small. Each of these problems is fairly small because we use, I don't know, polynomial degree, something like 7 to 10. And the measures are, I mean, you see here, it's not that many elements.
Okay. And there is in the chat from Squire says, please give boundary equation for L-shaped colored solution.
Boundary, sorry, can you run this by me again?
Please give boundary equation for L-shaped colored solution. I don't know what this means. Okay. Boundary conditions or?
Well, the boundary conditions are 0.
Zero,
it's the same problem we solve. It's always Dirichlet conditions.
Yeah. So homogeneous Dirichlet boundary conditions, right?
Yeah.
Further questions? At the very beginning, when you introduced the fractional Laplacian, you gave the different possibilities of defining it, and one was via the eigen decomposition of L. If you would have a different basis for characterizing, let's say, standard Sobolev spaces like wavelets or whatever, could you then also define the S power by that, replacing the eigen decomposition, the eigen functions?
I have not, must admit, I have not thought about that. But I wouldn't be too surprised if you could do that. But I need to think about that.
Yeah. Because in connection with that, the next question would be, is there anything known about optimality when you compare the error with respect to the best approximation given n degrees of freedom?
I mean, you're asking for an n-width result.
Right, something like that. Is there something known for those kind of problems?
Yes, there is something known that actually goes back to a very old paper by myself.
Good.
Well, essentially, these are elliptic problems. So you have a nice isomorphism between. If you look at you have a nice isomorphism between the energy, so the solution and the right-hand side F. And so as soon as you know how well you can approximate the right-hand side, as soon as you have an n-width result for the data, you can, by this isomorphism, create an n-width result for the solution. But of course, then the approximation space is kind of funny because it will be the pullback from a good space for the data.
Yeah.
But so, for example, a result is that if the data are analytic, the n-width result gives you exponential convergence with a slightly better exponent. So we got something like n to the what was it? N to the 1/6 for polygons, and you should, for polygons, you should actually get to n to the -1/2. So there's some room, But of course, then these spaces are not piecewise polynomial, so it's not quite clear what to do.
Okay. Good. Further questions? One point I did not quite get. I mean, you made it clear that there is a difference between the geometry of the domain and in elliptic problems we know that these reentrant corners are an issue. Are there any kind of restrictions to the shape of the domain? Because you said polygonal domain, but it could then be more or less arbitrary.
Yes, well, technically, I mean, curvilinear polygons are allowed too. So that is something that I did not emphasize, but yes, that is possible too. The slit domain is technically speaking not allowed, but I'm pretty sure the theory could be generalized to that. I mean, you see, in a way, we went about proving this. We went about it in a roundabout way because we use singular results for singular perturbation problems, and this is the tool that we had. So that is also limits here the result that we can prove, Dirichlet conditions and 2D, because that's what we use. In principle, of course, what should hold is that the extension problem one should be able to write down, one should be able to characterize the solution in terms of, well, these Babushka Guo spaces, so these countably normed spaces. One should be able to do that, but I mean, this is a hard task. I mean, a full proof is not yet given for the classical Laplacian. I mean, we're all waiting. And here, we have weights, right? I mean, it's not even a nice elliptic operator. So this is why we took the detour using this decoupling technique.
So you would need to consider weighted Bezoff spaces or whatever. So
yes.
I guess fun, yeah.
It's feasible. It is feasible.
Okay, good. Further questions? So this does not seem to be the case. So then let me thank Markus once again for this very nice talk. You see also in the chat, Colin was saying fantastic presentation. So just that I forward that piece of information to you, Markus, and then I would hand over the mic back to Stanley, I guess, right?
That about covers it. Thanks everybody for coming. Very, very interesting talk. And please join us next week. We have a talk by actually my colleague at Florida Tech, Kanishka Pereira. I just put the title of the talk in next week's talk into the chat. So yes, thanks again, Markus, and thanks everyone for coming.
Thank you.
Bye.
Bye.